Okay, I've got two definite integrals up here on the board. For both of them, the integrand, which is the function inside that integral sign that I'm thinking of as the height function, is the same. It's sine x. The difference is one of these I can do with the skills that I've taught you up until this point in the semester, and one of these I can't do with those skills. So what I want you to do is pause the video, draw the picture of the signed area that each one of these represents, figure out which one you can do, and do that one, and then tune back in. Welcome back. So, I'm going to sketch sine of x. This would be over the interval from 0 to 2 pi, where pi would be that point right in the middle. So this integral would represent this signed area. This bump, which we would count as positive, and this bump, which we would count as negative because it's below the x-axis. This integral, I'm not starting until pi, still ending at 2 pi. So this integral would just be this area right here, which would be negative. That's not a geometric shape that I know, so I don't have a formula from geometry for finding that. Now, I don't have a formula from geometry for finding either of these either, but I do know that they're exactly the same, but opposite in sign. So here, this is going to be 0 because this positive signed area will cancel with this negative signed area. So sometimes, even if I don't have a geometric formula, the notion that this definite integral represents signed area is enough for me to figure out what it is. Here, not so much. But here we can build on what we did in the previous section. In section 5.1, I can use Riemann sums to approximate signed area. So in 5.1, we were using Riemann sums to approximate area because our heights were always positive and our areas were therefore always positive. Now, I'm just going to use a Riemann sum to approximate a signed area. So the basic idea is that I'm going to chop. So I'm going to chop my interval up into little pieces, and that will induce a chopping of the area into little strips of area. I'm going to approximate. Now, instead of approximating the area of each piece, I'm going to be approximating the signed area of each piece. So what's going to happen is if I have a piece that looks something like this, where that's a curved thing, and this is a delta x here, I'm going to pick some representative x value and take the height at that particular point. And I'm going to approximate that the area of that strip is the same as the area of the rectangle that has the same base, still delta x, but has as its height f at xi star. X because it's an x value, I because it's going to be part of the ith subinterval, so if it's the 17th subinterval, I is 17, and a star to indicate that it doesn't necessarily have to be the right endpoint. Because when we do our chopping, when we partition the interval up into little pieces, we call the endpoints x sub 0, x sub 1, x sub 2, so that x sub 17, that name would already be taken for the right endpoint of the 17th subinterval. Okay. Now, I would approximate this area then as delta x times f of x sub xi star. This is allowed to be negative. So we're allowing our heights to be negative. So if the area that we have is below the x-axis, that's because our function is negative there. We'll be approximating it as a negative signed area. Okay. And then, of course, we'll just add those things up. So we'll have the sum as I goes from 1 to n of f of xi star times delta x, where n would just be the number of pieces into which I've chopped things. And we can say that this is an approximation then of the signed area between f of x and the x-axis. And of course, a sum like this, we call that a Riemann sum. So we spent a lot of time working on this in section 5.1. The only difference was that then we were requiring our function to be positive, so that what we were finding was geometric area. Now I'm allowing my function to be negative, so that what I'm finding is signed area. In the case of motion, we were requiring that our velocity was positive, so that it was the same as speed. And if you integrate speed, you get the distance that you've traveled. Now that I'm allowing my velocity to be negative, I'm no longer calculating a distance, I'm calculating a displacement. Because I might get some positive area when my velocity is positive and some negative area when my velocity is negative. And there, that's stuff canceling out. Because if I walk in this direction, and then I turn around and I walk back in this direction so that I'm back where I started, my displacement is 0, because the negative displacement and the positive displacement canceled each other out. Okay. All right. Of course, if I want to get the actual area instead of just an approximation, we add a step 4 to things. So step 4 would be to take a limit. So we'll say the limit as n goes to infinity, and assuming that I've used a regular partition, so that this is just b minus a over n, that's the length of the interval that we have. If n goes to infinity, that base is going to be going to 0. Of the sum as I goes from 1 to n, f xi star delta x. Okay. So we spent a lot of time in section 5.1 doing these first 3 steps, but with functions that were restricted to take on non-negative values. We're going to review that a little bit here now that our heights are allowed to be negative, but then we're going to transition to really focusing on this 4th step, taking the limit so that we get not just approximately, but exactly the definite integral. And you can sort of start to see where this notation comes from. Delta x, when I take the limit, becomes a dx. In my Riemann sum, I'm evaluating my height function at a representative x value. In my integral, I'm just integrating the height function. Here I was adding and taking a limit, so this integral sign really is saying add and take a limit. It's just sort of consolidating those 2 things into one and writing that as that squiggly integral sign. Okay, so before we actually do get to taking the limits, let's do a little bit of review of just some finite Riemann sums. So let's try to approximate this integral right here from pi to 2 pi of sine of x dx. Okay. So I'm going to approximate. I'm going to use a regular partition. I'm going to let n equal 3, so I'm going to chop it up into 3 equal pieces. So I'm going to have 3 signed rectangles whose signed areas I'm adding up. And let's use right endpoints. So again, as within 5.1, common choices for my representative x values, or my sample points, are right endpoints or left endpoints, midpoints. If I want to create an upper sum, I'll choose the x value where my function is at its highest value. If I want a lower sum, I'll choose the x value where my function is at its lowest value. And I'm allowed to just choose points at random. Just say I need a point in this subinterval, and I can just pick any of them. Okay. All right, so I'm going to draw myself a picture of this interval from pi to 2 pi. Now the length of that interval is pi, 2 pi minus pi. So my delta x is just going to be pi, the length of the interval, divided by 3. Okay. So I'm going to start at pi and just count over by pi over 3. So it may help for me to think of this as this is 3 pi over 3. So then my next point would be 4 pi over 3, and then 5 pi over 3. And sure enough, 2 pi is the same as 6 pi over 3. Okay, so I can mark off those points here, and that induces a chopping of this into 3 little strips of area. Now, I like to sort of have a table of values where I'm going to list my right endpoint and then my function at my right endpoint. So that's going to be 4 pi over 3, 5 pi over 3, and 2 pi. Don't include pi, that's not a right endpoint of anything. I've got 3 things here. I don't want 4 things in my table. 4 endpoints goes with 3 subintervals. Okay, so all of this, if we're going from pi to 2 pi, all of this puts me in either quadrants 3 or 4 where sign is negative. And I can sort of see that. So all of my heights are just going to be negative. Okay. So let's see, 4 pi over 3 would be here with a reference angle of pi over 3. And so if I evaluate sine there, it's negative because we're in quadrant 3. The reference angle is pi over 3, which is 60 degrees. So if I look at my 30, 60, 90 triangle, sine of 60 is root 3 over 2. So that's going to be a negative root 3 over 2. 5 pi over 3, very similar, except now we're in quadrant 4. But the reference angle is still pi over 3, so it's going to be negative because we're in quadrant 4, root 3 over 2. And then at 2 pi, sine of 2 pi is just 0. So if I want to draw in the rectangles that I get, here's my first subinterval. This is my right endpoint. Here's the height that I'm using. I'm going to extend that over that first subinterval, and so I'm getting this rectangle, which includes some extra negative area. Okay. Over this next interval, here's my right endpoint. Here's the height there. I'm going to extend that over the interval. Looks like we're missing just a little bit of negative area, because the low point would be at pi over 2, which is in between those endpoints. And then third interval, here's 2 pi. Ooh, there we're missing a lot of negative area. We're getting a degenerate rectangle in that case. Okay. So I can now say that this definite integral is approximately, let's see, we've got negative root 3 over 2 times pi over 3. That's a height times a base. Plus negative root 3 over 2 times pi over 3. That's a height times a base. Plus 0 times pi over 3. That's a height times a base. Of course, I can factor out that common base of pi over 3. And if you're comfortable going right to that, it's totally fine. It's pi over 3 times negative root 3 over 2 minus root 3 over 2 plus 0. So that's just going to be, that's 2 copies of negative root 3 over 2. So that's just negative root 3. So I get negative root 3 times pi over 3. That would be this estimate that I get using a Riemann sum now to estimate signed area rather than just estimating purely geometric area.